Hello and welcome to the last of 3 bonus videos in which I've been rebuilding experiments from this book, Charles Platt's Make Electronics 3rd edition, but using various microcontrollers instead of the original analog circuits. And in today's video, I'm going to be rebuilding the alarm circuit from experiment 17, but using a Raspberry Pi Pico development board instead of the analog circuit. And this is from the same people who developed the very popular series of single board computers, the Raspberry Pi. But this board is using their own microcontroller, the RP2040. And as you can see, it's a very similar form factor to the Arduino Nano Every that we used a few videos ago. Now, one thing to watch out for if you're purchasing these is that they are in fact available in 2 versions. So this is the standard version, but you can also get one that has a Wi-Fi capability, which is a little bit more expensive. And you can tell if it's that one because it has this extra shielded chip that you can see here for the Wi-Fi. The other difference is that both versions are available in 2 formats. One is just with these solder pads for the pins, and obviously this is useful if you're soldering it into a final project, but you can also get a version with header pins already soldered into place, which is much more useful if you're prototyping and experimenting and you want to put it into a breadboard, as we do in this case. Also, we don't need the Wi-Fi for this experiment, so I'm just going to use this standard version with the header pins. So before we get down to building, let's just have a quick reminder of the original analog circuit.
So here's the finished item, all boxed up. For the purposes of this demonstration, I'm just hooked up to a single reed switch, but obviously you could have several of them in series. So the power supply is connected, so let's just fire it up. And there you can see the light coming on to indicate that we've got all our windows and doors closed at the moment, which is good. So if I want to leave the house, I can press the button, the other light comes on to say I've got a limited window of time. So during that time, I can open the door and close it again so that I can leave the house. And I'll just fast forward past the delay, which is a little over 30 seconds. So now the warning light has gone off. So now if a door or window is opened, you can see that connection is broken because our ready light has gone off. And now again, we've got a limited amount of time to disable the alarm. And if we don't disable it in time, and again, I'll fast forward past the delay. And there we go, our alarm has gone off. So that's everything working as it should do.
Before building the new circuit and programming the microcontroller, it's useful to review the controls on the original analog circuit and decide if I want to make any changes. Let's start with this switch. All it does is interrupt the power supply to the circuit. It's just a simple on-off switch. If at some point I want to make this new digital version into a boxed project like the analog circuit, I can take exactly the same approach and place a switch between the power supply and the Pico. So for the breadboard prototype, I'm not going to include this switch. This LED monitors the status of the reed switches on the doors or windows. If any switch in the chain is open, this LED is off, otherwise it will be lit. This is important so we can see if everything is shut before setting the alarm, so I'll keep this functionality the same. This push button is used to set the alarm. In the analog circuit, disarming the alarm is achieved by switching the circuit off. One reason for that is the difficulty of getting one button to perform context-sensitive functions in an analog circuit. But in a digital circuit, that's comparatively easy. So I intend to use the same button to toggle between an armed and disarmed state and to cancel a triggered alarm. The second LED here comes on when the circuit is armed, to indicate the delay to allow you to exit the house. At the end of this delay, it goes off again. It will come on again if the alarm is triggered. Again, with a digital circuit, we can use a single LED more effectively to indicate different states. So my plan is that when this LED is off, that indicates a disarmed state. When the circuit is armed, the LED will start blinking slowly to indicate the leave the house period. Once that period has elapsed, the LED will be fully on and steady to indicate the circuit is armed. If the alarm is triggered, the LED will start blinking rapidly to indicate that an alarm is imminent. When this period has elapsed and the alarm is sounding, it will show alternate long and slow flashes. The final element is the alarm sound. In the original project, I used a separate analog multivibrator circuit linked to a loudspeaker for this. I can take a similar approach here, but for the purpose of prototyping, I'm initially going to add a third LED to indicate the alarm being activated. Now let's address the elephant in the room. Clearly, there are two fundamental problems with the circuit as it stands. Firstly, we can arm and disarm the circuit simply by pressing a button. In reality, we'd want something more secure, like a keypad, to enter a secret code. If you watched the previous video in this series, you will have seen how to wire up a keypad for just such a purpose. Secondly, even if we had such a keypad in place, currently the alarm can be disarmed simply by cutting through or removing the power cable. To prevent that possibility, we'd need to add a battery backup and a circuit to keep the battery charged and to monitor power and switch over to the battery as soon as the voltage on the main supply drops below a certain level. This would mean even if the mains power was interrupted, the alarm would continue to sound until the battery ran down. For the sake of keeping this video to a reasonable length, I'm not going to make either of those enhancements, but both would be highly recommended if you were building a practical alarm system. So now I know what components I need, I can build my initial circuit. So here's that circuit built, but of course it's not much use without a program. But before opening up the editor, it's worth spending a bit of time thinking about the best approach. First, this LED here is bound to the state of the reed switches. If the reed switches are open, then it's off, and if the reed switches are all closed, then it's on. So it's simply a case of continually monitoring the status of the reed switches and setting the LED to match. Things get a little more complicated with our other two LEDs and the disarm button. These can be in several states. We can manage these using something called a state machine, which models the different possible states and transitions between them based on inputs. And the three inputs of interest to us in this case are the state of the arm disarm button, the state of the timer used to control delays, and the state of the reed switches. So the default state is unarmed. From here, there's just one possible transition, and that's to an arming state, which happens when the button is pushed. When this transition happens, we set the LED to a slow blink, and we start the timer to give us time to leave the property. There are two possible transitions from this state. The first happens if the button is pushed again, which takes us back to an unarmed state. Here we turn off the LED before waiting for another transition. The second transition from the arming state happens if the timer expires. This will move us to a new state, armed. On the transition to this state, we set the LED to be fully on. Once again, there are two possible transitions. Back to the unarmed state if the button is pushed, or to a triggering state if the reed switches are opened. When the transition to the triggering state happens, we set the LED to a rapid blink and set the timer to count down, which gives us time to disarm the circuit if we entered the property legitimately. Once again, there are two possible transitions from this state. One back to the unarmed state if we press the arm disarm button in time, and the second to the triggered state if the timer expires. For the final state, triggered,
We set the LED to alternate slow and fast blinks, and we trigger the alarm noise circuit, which in this case is represented by just another LED, but will eventually be something that makes a sound. From this state, we have just one possible transition, back to the unarmed state if the button is pushed. Here we turn off the LED and silence the alarm. So that's the plan. Let's now look at the code. So here's the code. The Integrated Development Environment, or IDE, that I'm using is called Thonny, and it's a Python or MicroPython IDE for beginners. So it's a good place to start if you're using a Raspberry Pi Pico for the first time. But you can for sure use other editors if you prefer. MicroPython is essentially a leaner variant of the popular Python language, but one that's intended for microcontrollers. Generally, the first thing we'll do in any MicroPython code is import any libraries we need. Here you can see I'm importing from two libraries, machine and time, but I'm only importing a single item from each library. Pin is an object used to control GPIO pins, and tixms is a function that returns the number of milliseconds that have elapsed since power on or the last reset. The first thing I do in this code is define 5 classes to represent elements of the circuit, starting with the LED indicators. A class is a blueprint for an object that defines both data and behaviors. Classes and objects are aspects of object-oriented programming, or OOP for short. Note that the convention is for class names to have an initial capital letter. One thing to note here is that Python and MicroPython use indentation, and in Python it's not just a formatting nicety, it's essential because indentation is used to define code blocks instead of either curly braces as we saw with C or keywords as we saw with BASIC. So here, for example, I'm declaring a new class indicator. Everything below this line that has a higher level of indentation is part of that class. And that remains true until we have another line of code at the same level of indentation, which in this case is down here on line 45. The first thing that happens in this class is that I define 4 class attributes. Class attributes are data that are shared by all objects created from a class. Note that these particular attributes are not variables but constants, as indicated by the use of the const function here. The use of uppercase letters here also indicates that these are constant values. They define values for the 2 possible states of an indicator, on or off, and the duration in milliseconds of a short and long blink. The keyword def is used to start a function definition in Python. Note that here the code is entering another level of indentation. Everything indented to the right of this line belongs to the function. But because the whole function is indented, it also belongs to the class. It's referred to as a method of the class. This is a special method known as a constructor. It's required for every class, and it's run whenever a new object is created from this class. All methods in a class must have at least one argument, self. This is a value that's passed automatically when a method is called, and it points to the particular object running the method. For a constructor, I also need any arguments required to initialize the object. In this case, I need just one further piece of information, the pin number that this LED indicator is connected to. Within the body of the constructor, I use that to set the pin as an output and save the pin reference to an instance attribute. An instance attribute, unlike a class attribute, belongs to a specific object created from the class. This is why I need to prefix it with the keyword self and a dot, because I'm referring to a specific instance. Next, I run another method, off. Once again, I'm running that method against a specific object, so I need to prefix the method name with self and a dot. As you can see down here, off sets another instance attribute, state, to indicate the new state of this LED indicator. For the state value, I'm using one of the class attributes I set up earlier. Note here, because it's a class attribute and not an instance attribute, I'm prefixing it with the class name and a dot. It sets another instance attribute, blinking, to false to indicate that the LED is fully off and not temporarily off as part of a blinking pattern. Finally, I call the off method on the pin object, which will set the pin low and therefore turn the LED off. Above it is another method, on, which does the opposite. The blink method is called to set the LED into a blinking state. It expects to receive a set of values indicating the blink sequence. When you want to create a related and ordered set of values in Python, you can use a structure called a list. If I scroll down here to line 120, you can see an example of a list being passed to this method. Note that a list is contained in a pair of square brackets. The blink method expects a sequence of Boolean values. That is, they're either true or false, with false indicating a short blink and true indicating a long blink. Here, because I want both on and off blinks to be the same duration, I'm just using a single value. Down on line 133 is an example of a longer sequence. The values in the list will be consumed one at a time for off and on durations until the list is exhausted, and then the code will return to the beginning of the list. The sequence can be as long as needed, and individual values in the list are separated by commas. If I go back to the blink method, the first thing it does is switch the LED off and set the state to match. Now it checks to make sure it's received a list with some content and not an empty list. It does this using the len function, which returns the number of items in a list. Assuming all is okay, the pattern is copied into another instance attribute, and a further instance attribute is set up to indicate the current position in the pattern. Lists are zero indexed, which means the first list element is at position 0. Now I call tixms to get the time at which the blinking started. I'll make use of this later. Finally, I set the isBlinking instance attribute to true. Note that this method simply sets everything up for blinking. It doesn't actually do the blinking. This task is completed by the update method, which will be called in my main loop. Whenever update is run, it first checks to see if the LED is in a blinking state. If not, it's either fully on or fully off, so there's nothing to be done here. If it is blinking, I set a variable to be equal to the correct duration based on whether the pattern at the current position is true or false. Notice that this is not an instance attribute or a class attribute because it doesn't have a prefix. It's simply a variable that is local to the method, and it will only exist for as long as that method is running. Now I use this value to check if the time elapsed since the state of the LED was last changed has exceeded that duration. If it has, I toggle the state and set the pin value accordingly to turn the LED either on or off. I must now record the time of this change and update the position to the next one in the pattern. I now check to see if the end of the pattern has been reached. Remember, lists are zero indexed, so if the position is equal to the length of the list, then it's one more than the position of the final value. If this is the case, then the position is set back to the first item in the list. And that brings us to the end of this first class, so the code indentation goes fully back to the left. The next two lines create two instances of this indicator class, one for the LED that monitors the status of the read switches, and one for the LED that indicates the alarm status. The next class models the chain of read switches. Again, this is initialized with a pin number, but this time the pin is configured as an input pin with a pull-up resistor, because a fully closed path in the read switches will connect the pin to ground and pull it low. The final part of the initialization is to run the update method, which will also be called from within the main loop. This method sets a state attribute based on the current value of the pin. Note the use of not here. This is because the pin will be high when the switches are closed and low when they are opened, but I want the state to be the other way round, so that a high will indicate a broken circuit. Also note that I'm not concerned with debouncing for this type of switch, because as soon as the two halves of one read switch separate far enough to break the connection, no matter how momentarily, I want the alarm to be triggered. That's the end of the class definition, and now I create an instance of it mapped to the pin connected to the read switches. The next class models the ARM Disarm button. Here, I do need to be concerned with debouncing the button, so I set up a constant value as a class attribute with the debounce time in milliseconds, and I also set up an instance attribute to keep track of the time of the most recent change of state. If you happen to be familiar with another OOP language like Java or C++, you might have noticed that I've not been using any keywords to indicate whether attributes and methods are public or private or protected, and neither have I been creating getter or setter methods for attributes. In Python, attributes and methods are public by default, and attributes are generally accessed directly rather than via getter or setter methods. If it becomes necessary to use a getter or setter method, for example, because you need to do some additional processing before returning or updating an attribute, then there is a way to do this. A good example is the state of the ARM Disarm button. Note again that state is set to the actual pin value but inverted, so that a high state indicates the button has been pushed. However, I don't want to just return the raw state of the button. Why? Because during the time the button is held down, the main loop will have run many times, but I only want that button push to be registered once until the button is released again. That means I need to process this attribute to make sure that a high state is only sent once per button push. To do that, I first make the state attribute private by prefixing it with a double underscore. I now create an instance method that will be treated like an attribute. To do that, I use something called a decorator to mark this as a property. A decorator takes a function and adds additional code behind the scenes to give it certain behaviors. In all other respects, this is defined as a normal method with a return value. Notice that here, the return value, rather than just being the current state, uses Boolean logic to combine it with another attribute, read, which will be true if this high value has already been read. So the net effect of this statement is, if this object has a high state and has not yet been read, then return it. In all other cases, return a low state. Note that if it is returning a high state, then the read attribute is set to true, so that state cannot be returned again until the button has been released. Moving on to the update method, which will be called from the main loop, this gets the current pin value and inverts it as before. It then checks if the current pin state is different to the last recorded state, but also whether sufficient time has passed since the last state change. This is in effect our debouncing of the button. Assuming both these conditions are true, I change the state of the object. If it just changed to a low state, then it's safe to clear the read attribute so that the next high state can be read. And of course, the time of this change needs to be recorded for debouncing. So that's the end of this class, and now I create an instance of it mapped to the pin connected to that button. The third class models the device that gives the audio visual alert when the alarm is sounding. For this prototype, it's just an LED, but eventually it will be something that makes a noise. This one is pretty simple. It just has methods to turn the alarm on or off. Finally, we come to the class that models the state machine for the alarm manager. You'll see the different states are given values as class attributes. I also set the duration of the two delays for the exit timer and the alarm timer. Now here's one of the great advantages of digital circuits. In the analog circuit, these delay times were set by the values of a resistor and capacitor in an RC circuit. So to change those times would involve swapping out those components. In a digital circuit, if I want to change those times, I can do so simply by updating these class attributes. For the purpose of prototyping, I've set them both to 5 seconds. If I eventually create a boxed circuit, I can set them to something more practical, like 30 seconds. When the object is initialized, it sets the state machine to the default state, unarmed. The update method, that's called in the main loop, has an if-elif, that's short for if-else-if, structure that executes the required code for the current state. Each segment of code in this structure will check for conditions that trigger a transition to another state. For example, while the object is in the unarmed state, it needs to look for the armed disarm button being pressed. If that happens, it runs transition code which sets the new state, arming, starts the exit timer, and sets the LED to a slow blink. A similar pattern is followed for the other states. Note that one of the transitions, the one that goes back to the unarmed state, is shared by several states. So for this transition, I created a check for disarm method that monitors for the button press and manages the transition, then returns true if the transition has been triggered. This can then be checked for in each of the states where it's needed. That's the end of this class, so now, as before, I create an instance of the class. So that's all the objects set up. So now the code can enter the main loop. This makes use of a type of loop called a while loop. This checks a condition and only runs the code within the loop while that condition is true. Here though, I want the code to run forever, so I create an infinite loop by using the Boolean value true instead of a condition. Within the loop, I first update the states of the read switch chain and the arm disarm button. I then set the indicator light for the read switches on or off based on the current state of those switches. Next, the alarm status LED is updated. Finally, the state machine for the alarm manager is updated. This technique of continually checking the status of sensors in a loop is known as polling. There is another approach which makes use of interrupts, where, for example, a change of state in a pin can be used to interrupt the current process to run an interrupt handler. I've used polling here because it's easier to understand. However, it's not very efficient and can consume more power than a program and circuit that makes use of interrupts. So as you get more proficient with programming for microcontrollers, interrupts is definitely something you'll want to explore.
So I've downloaded the program to the Pico. So now we can give it a quick test. So at the moment you can see the read switch is open. So this indicator light here is off. But if I move the two halves together to close that switch, then this indicator light comes on. That means we're ready, all the doors and windows are closed, so we're ready to arm the circuit, which I can do with this button here. And I can also at any point press it again to go back to that disarmed state. But let me now run through the sequence. So press it once, we go into arming. I can open and close during this phase. At the end of that arming phase, that indicator comes on fully, which means that we're now in an armed state. At this point, if the read switches are broken anywhere, which I'll do now, you can see that starts flashing to indicate that an alarm is imminent. And when we get to the end of that phase, the alarm is turned on, indicated by this LED coming on, and we then go into a sequence of long and short flashes on the control board to also indicate that the alarm has been triggered. At this point, even if I close a door or window again, it isn't going to make any difference to that alarm being triggered. The only thing I can do at this point is to press the disarm button again to go back to a disarmed state. Now, of course, at the moment, the way this is working is when the alarm is triggered, all it's doing is switching on this LED here. But of course, what we really want is to have some sort of audio or audio and visual alert. Now, if you watch the first of these bonus videos, you might recall that in that video, we were using this, the BBC Microbit, and we programmed it to do this. So it struck me that that will serve as quite a nice audio and visual alert when the alarm is triggered. But of course, that does raise another question, which is how do I get the Pico to talk to the microbit to tell the microbit when to trigger that alert? And of course, that is going to involve making some sort of wiring connection between the Pico and the microbit. Now, here's an interesting thing about the microbit. It's a bit unusual as far as development boards go, because whereas something like the Pico has everything bored out to header pins, which of course you can't see at the moment because they're plugged into the breadboard, the microbit has this edge connector, and that's how you get access to the GPIO pins on the microcontroller. But you can see these connectors are very narrow. There are 3 GPIO pins which have a wider connector. Potentially you could access by just clipping an alligator clip onto those, but that's not a particularly stable way of making a connection. So if you want full access to everything, you will need to get hold of something like this. This little add-on board is a third-party board. I picked this one up, I think, for slightly less than £10 in the UK. And you can see it has an edge connector that the microbit plugs into, and then it brings out all of the GPIO pins onto header pins, which makes it a lot easier to make those connections. So what I'll do is I'll set this up, I'll make my connection to the Pico, and then I'll explain what I've done before we move on to some additional programming. Now, before you go hooking up one microcontroller to another, there are a couple of really important things to take care of. The first is to check what logic levels is each microcontroller using. Now, in this case, we're lucky because both the BBC microbit and the Pico both use a 3.3 volt logic level. However, if we'd have been connecting the Pico up to the pickaxe system, which we used in the second of these bonus videos, that uses a 5 volt logic level. So in this case, we wouldn't have been able to connect them directly. We would have had to have used something called a logic level shifter to be able to safely connect them. In this case, because both boards are using the same logic level, it's unnecessary to use that, so we can make a direct connection. But the other thing we need to do is make sure that there is a shared ground connection. And you can see that I've connected to one of the ground pins on the microbit to the ground rail on the breadboard here, which of course in turn is connected to a ground pin on the Pico. It's very important to have that common ground connection so that there is a common point of reference, because otherwise, even though they share the same logic level, that's 3.3 volts, but 3.3 volts relative to what? If your reference for that 3.3 volts is different on each board, then it's possible that what one recognizes as a high signal might not be recognized as high by the other. So having that ground, that common ground connection is very important to get that common reference point. Okay, so the next thing is, how do I send a signal from one board to the other? If we were doing, in this case, any kind of complex messaging, or if we wanted to send messages back and forth between the two boards, then it would be necessary to use a serial communication protocol, something like Universal Asynchronous Receive Transmit, or UART for short, or I2C is another one that you can use, or SPI. However, in this case, all we're doing is telling the microbit either you've got to be sounding and showing the alarm at this point, or you've got to have stopped the alarm at this point. Just 2 states. And we're not worried about getting any kind of acknowledgement back from the microbit. And if you think about it, those 2 states can be conveyed using a single bit. So in this case, a serial protocol is kind of overkill. All we need to do is to connect one GPIO pin on the Pico to a GPIO pin on the microbit. However, having said that, one thing we do need to take care of is to ensure that we've programmed both boards correctly so that the pin on the Pico is an output pin and the pin on the microbit is an input pin. If we try to connect, for example, 2 output pins together, then we might be getting into a bit of trouble. So it's well worth just checking your programming if you're going to connect them in this way. So I didn't really need to make any changes to the Pico side of things because we already had that pin driving that LED. So that pin is going high when the alarm is on and it's going low when the alarm is off. So on the microbit, I need to set the pin as an input pin, and I need to pull it low with a pull down resistor so that its normal state is low and it will go high when it receives the signal from the Pico. So let's have a quick look at the changes that I've made to the program on the microbit. So the first thing I've done is when we start up, I've set the pin that I'm using on the microbit to have a pull down resistor. Now over here in our main loop, I've basically taken all of the code that was in there before, which is from this play block here right down to the end of this for loop here. And I've put it all into another loop, a while loop. And basically that while loop will check to see whether pin 16 is high, or in other words 1. And if it is, all the time that it is in that high state, it will loop through this code, which will show the lighting sequence and the alarm sound. As soon as pin 16 goes low, which of course it will do when the alarm is turned off, we'll drop out of the bottom of that loop. And at this point, you'll see I've got two commands here, one to clear the screen. In this case, screen is the block of LEDs on the microbit. So we just want to make sure that those are all off, and we want to make sure that no sound is playing, so we stop all the sounds. And then we go into another loop, and we will remain in this while loop all the while that pin 16 is low. In other words, while it's off on the Pico. And in this loop, all I do is pause for 100 microseconds. And basically what that means is while we're in this loop, we'll be checking for the state of pin 16 10 times every second, which is enough. That's a high enough resolution for checking that pin for something like a security alarm. And of course, as soon as pin 16 goes high again, we'll drop out of this loop, which brings us to the end of the main loop. So we'll then go back to the top, and then because pin 16 is high at this point, we will go back into this while loop, and the alarm will sound, and so on and so forth forever. So that's the theory. Let me download that code to the microbit, and then let's see if our two microcontrollers are going to behave and work well together. Okay, here we go. So the light's on, so our doors and windows are closed. So I can arm. You can see that's flashing to say that we're arming. We're now armed. So now at this point, if a door or a window is opened, see we go into alarm is imminent. And there we go. The alarm has now been triggered. Control board is showing that alternate long and slow flash, and our alarm is of course sounding, and it will continue to sound. It doesn't matter once again if we close the window at this point. The alarm will continue until we press the disarm button, and then it will stop. So there you go. That's a very simple way to get two microcontrollers to cooperate with each other.
And that sadly brings us to the very end of this series, and I do sincerely hope that you've enjoyed the videos and you've got something out of them. And if you're planning on actually building the experiments, then I do strongly encourage you to invest in a copy of the book. It's available in both paperback and in electronic versions. It goes into a lot more detail than I have in the video. There's a lot more background information. There's the full circuit diagrams, the component schedules, all the breadboard layouts that you'll need to successfully build those experiments. And as I've said repeatedly throughout this series, I'm not in any way connected to the publisher or author. I'm not getting any kind of incentive from them to promote the book. I just think it's a great book. So where do we go from here? Well, it makes sense to me to kind of continue what we started. So I am planning on doing a very similar thing with this book, which is the follow-on, Make More Electronics, again by Charles Platt. So that should be a lot of fun. So I'm looking forward to that. But I'm also going to divide my time between that and another book from the Make stable, which is this one, Make Radio. This is a more recently published book. And as a radio amateur, I'm always looking to increase my knowledge of the theory and construction side of things. So I thought, yeah, I'll give this one a go as well. So look out for both of those series starting in the very near future. And so with that, it just remains for me to say thank you very much for watching, and until next time, farewell.